So, as we saw in the solver, if we pick too large of a time step, it leads to issues. Can we think about what might cause that? Well, we saw that if our time step is too large, if we decrease our elements, number of elements in our domain, and therefore increase our element size, it fixes the problem some. And so we can think about what's actually occurring in an advection. Imagine that we have some sort of global domain that we discretize spatially, and we have some sort of parcel that we're looking at the advection of. So this would be our Q here. We need to make sure that we're capturing Q on a particular element. So imagine that our velocity is such that in 1 second we travel one element. Well, if we choose our time step to be greater than that velocity, then what would happen? Well, our parcel would move greater than one element. And if we choose it too large, it could skip a whole bunch of elements. And this is a problem because we're not properly resolving our solution and the other elements along the way. So this is what's essentially happening is when we have too large of a time step, if we decrease our number of elements, we're increasing our element size such that we can imagine now our new element size is this big. So originally this would have gone too far. Now it stays within the same element, and so we avoid the problem. So how can we express this? Well, there's something called the current Friedrichs-Lewis condition, and this essentially is just a expression of the distance traveled by a parcel compared to the size of an element. So here's the distance traveled, right? Our velocity times our time step. This is the distance traveled by a particular parcel, and this is the size of our element. If this quantity is greater than this quantity, it means we've bypassed at least one element. So we need to make sure that this is at worst equal to 1, and ideally a little bit smaller than that, or quite a bit smaller depending on the nature of the problem. So what we say is that the CFL number has to be 1 or less. Now this is the case for an explicit time integration, so our forward Euler that we're using, and even the Runge-Kutta fourth order time integration we'll use in Module 3 also has this issue. Implicit solvers, because of the nature of how they're calculating the future time step, can have CFL numbers greater than 1, depending upon the stability of the time integration, or the time discretization technique. Okay, so this completes the analysis of our simple 1D linear solver. I would recommend that you look over the example 1D solver code that we just examined and see if you can modify, or even better, see if you can take what you've learned in these lectures and build your own solver by yourself. Don't be afraid to take a peek at the example code if you get stuck, but you have all the machinery to be able to implement your own 1D solver.